So it hit 11 o'clock. I'm going to go ahead and start this. It's being recorded. If you have other people in your facility that you feel might want to see this, we can send you the recording or, like I said, do another presentation for you guys. So we're going to do leak repair. To stop a leak, normally what we use is composites. So we're going to go into composite theory. Then we're going to go into some live sealing and some leak prevention applications. So what you're looking at here on the left, that is our Belzona Super App 2, which is a ASME engineered composite. And we'll go into how these types of systems work and how to make them work correctly to stop that leak. So what is a composite? So everyone deals with composites every day. One of the main ones that you're going to deal with the most is going to be concrete. So concrete rebar is added to concrete to increase tensile strength. So we do a similar thing with our products. Is the epoxy resin on its own is not going to stop a leak or do anything. So we'll combine it with a carbon fiber or fiberglass composite, which is going to make it have pressure retention and increased tensile strength and stiffness. And what you're doing is making a secondary wall out of the carbon fiber or fiberglass composite mixed with epoxy resin. So all composites will have a matrix phase and a disperse phase. Uh, Pretty much you're going to have, you have cement or Portland cement mixed with the rebar. So the rebar is the fibers and the Portland cement is the matrix. So in our case, we have an epoxy matrix with a carbon fiber um, disperse phase, which is the fibers. So the fibers is what gives it the strength, and the epoxy is what allows it to stick to the metal and also gives it the chemical and temperature resistance. So it's definitely the composite industry is growing. It's widely accepted in a lot of industries. It's still There still is a pushback. We still get the pushback at times. Does this work? Does it not work? Well, there's so much composites in everyday life, anywhere from aircrafts to military equipment. So it's very proven industry and very growing industry. With composites, you're gaining a lot with materials by combining two different materials and getting the best of your carbon fiber with the best of your epoxy. So you're making your epoxy stronger, but you're allowing your carbon fiber to stick to metal. Um, so it's definitely a growing industry, growing technology. You're seeing a lot more. When I say FRP, that's going to be your composites. So you see a lot of FRP tanks, vessels, pipes, just pipes made out of fiberglass. So that's a fiberglass reinforced plastic. A lot of repair of equipment with FRPs, and you're seeing a lot of wind turbines are made out of this. So that's when you see those big wind turbines going down the highway. Those are made out of fiberglass. So we're even making equipment out of it nowadays. So it's definitely already a big industry and growing every day. So it's a lot of science to back it up, a lot of engineering, a lot of testing, and we use it quite a bit. So what we have in Belzona is going to be the main one we're going to use is our ASME engineered system called Belzona Super App 2. It uses a dry reinforcing cloth. The cloth is made out of carbon fiber and fiberglass in a specialty pattern that gives it strength in certain directions that it needs. So everything is tailor fit uh, to basically reinforce piping, pressure vessels, and tanks. Our resin system, which is the matrix part, is going to be an epoxy. There are some systems out there in the market that use polyurethanes and different resin systems, but the main one we use is going to be epoxy. The great part about this system, and if you're looking at this application here in the top left, is it's moldable. So it's a dry cut cloth. You can fit it to whatever geometry you need. So it's cut to size in the field, and the resin allows it to mold around any geometry. You can do patches, you can do wraps, you can go over tees, bends, different geometries. So it's always customizable. You don't have to fabricate anything offsite. It's ready to go out of the box. It's laid up in the field wet, as you can see here. So this is the cloth, and the resin is being used to saturate it. And once you saturate the resin, you can wrap around a acid, and then once it cures, it forms an outer pipe, basically outer wall that reinforces the pipe wall and actually can contain leaks. So how do we use this system to contain leaks? Let's say we have a substrate here, we have a hole that you're looking at here, and the outer top part is our repair laminate. So the first thing we have to ensure is that our adhesion is strong enough so that the leak just doesn't come out the edges of the repair. So um, once you basically the way you do this is first off you use the correct system that has the correct data, correct adhesion. You look into the pressure of the system, you look into your adhesion testing, and then you prepare everything as per the recommended instructions for use. So for high pressure leaks, we're going to want the best type of surface prep, which is abrasive blasting. We do have minimal surface preparation products in which if you can abrasive blast, we can get it done with a lesser prep. But basically, the higher the pressure, the better you want your surface preparation to be. So once we wrap over or put a composite over an acid, a substrate that has a hole, first thing this hole is going to want to do is come out and try to go out the bond line. So we got to make sure that first off, we have some bonding area beyond the hole. You don't want to land right on the hole, and that we have good bonding so that the fluid can't shear its way out the edges. Next thing we want to look into is that the cohesive strength is greater than the pressure force applied. So whatever we put on top of the hole, we want to make sure that the pressure just can't just go through it. The way we achieve this is by applying multiple layers to overlap plies or joints and to build up the composite to the proper thickness. So with our ASME engineered wrap, we can actually calculate how thick it has to be to hold in the pressure coming out of the hole. So that's a good thing with the ASME engineered wraps that's actually calculated. We have a lot of other systems that have extensive testing, so we know how thick it has to be to have that cohesive strength. And that's why we use composites so that we increase the tensile strength and the cohesive strength of the composite to make it allow it to be able to hold in the pressure coming from the leak. So same thing you would do with concrete and rebar. You're making it stronger so it can handle more loading. Also, for long-term success, you're going to want to make sure that the temperature is within the limit of your whatever system you're using. So if you have a leak of a pipe that operates at 300, you want to make sure that that product can handle 300 degrees F. So you want to make sure that if it does get exposed to 300 degrees F, what's going to happen to the strength? As you can see, our high temperature products, we're going to test the tensile strength at 300 degrees. We're going to test the Young's modulus at 300 degrees. We do adhesion testing at 300 degrees. We have to see what kind of degradation of our properties are we going to get at those elevated temperatures. And then there's also specific heat distortion and heat resistance testing that you can do. HDT, his heat distortion temperature, is one of the most popular and common. So this is where you have a cast sample and you put it in an oil bath, put a constant load on it, and you raise the temperature until you see some deformation in the sample. So that's when you know that you're starting to lose some mechanical strength. So we got to understand, like at this temperature, how much mechanical strength are we losing? Then we look at the pressure and say, hey, that's, we're going to have enough strength at that point to contain this leak long term. And then finally, you're going to want to look at the chemical compatibility. If you have enough strength to hold in the leak, enough enough thickness to hold in the pressure, you can handle the temperature, you do everything right, but then you can't handle the chemical, it's not going to work long term. So we got to make sure that whatever chemical is being exposed to the repair is not going to cause issues like you see here on the far right. So this is one of the standard tests we use in ISO 2812-1. This is where we coat rods with our product and put them in test tubes with different chemicals and see how they react over a full year. So if they are not, if there's no damage after a full year, then they get an excellent rating. And then, if there's any damage within that year, they get different ratings, and we can see, we might not be able to handle that chemical, or we can handle that chemical. So these are the main things you want to do. You want to do to make sure you can hold in a leak long term. And now I'll go into some examples. So I'm going to start out with some examples that are offline repairs. So they're leaking. The acid was taken offline. We repaired it, and then the acid was put back online. So this is a tank floor that was leaking from several different locations. The leak locations were unknown, but you could see the leaks from the outside of the tank while it was in service. The leaks were coming underneath the tank. So they shut down the tank, cleaned it out, and what we did here was we installed a composite fiberglass floor across the whole tank floor to make sure that we got whatever leaks there were. The good thing, like I said about composites, a growing industry, but it also has a long history. So a lot of API standards are going to have um, FRPs and ASME engineered wraps as approved repairs. And API 652 has statements that say stuff like this, like a reinforced FRP laminate can bridge perforations up to 8 inch, up to 82 psi. So here we got a lot smaller defects than 8 inch and lower pressure than 82 psi because we're only dealing with head pressure of a 12-inch tall tank. I mean 12-foot tall tank. Sorry. Um, so here we know that it's an approved repair with API. We've done it several times. It has good success. Actually, a pretty minimal risk application for a composite liner when they were really built for high pressure applications such as midstream piping. So fairly easy application. We put a fiberglass composite over the whole tank floor. We made sure that it could handle the chemicals. We made sure that it could handle the temperature, and we made sure that all the preparation was done as per the instructions for use. So it was installed, allowed to cure, tank put back into service, no further leaks. We also, what we like to do is have full procedures, really go through all the survey reports, so make sure we understand this is operating at 210, this is the chemical, this is how we're going to fix it, this is the product, this is how many layers are going to be required. So that's how you really can have a lot of reliability with your repairs. So going into some different assets. So instead of the tank floor, we're looking at the tank shell here on the molten sulfur tank. So our ASME engineered wrap, which is Belzona Super Wrap 2, is an approved API 653 repair as per API 653. So this was installed. There was about a 2-inch gash in this molten sulfur tank due to a steam coil leakage. So we came in, they lowered the level of the tank. We were able to do our repair. The next day, they were able to rise the level of the tank to the correct level. ASME engineered wraps, as per Article 401, are also approved as per API 510. On the right here, we see a steam stripper that they also had a large gash due to a steam inlet line. This one they had to shut down. During a small shutdown, we came in and performed our wrap patch, as you see here. And when it was fully cured, they put it back into service. So they stopped that leak there out of service and put it back into service. And then another, this is another example here. This is something that's we've seen it quite a bit. Cracked fiberglass flanges, but in general, gasket repair and flange repair are pretty common out there. So this is one where the flange was over torqued and it actually cracked the fiberglass flange. So they were going to have some sealing issues. They came in and replaced the bottom spool, but the top here fiberglass flange you can see here still had a crack. So they needed some sort of solution to really create this flange face again and make sure this is sealed correctly. So we came up with a solution. We know our products stick to fiberglass. We have a certain prep that we like to do with fiberglass. So we glued in the bolt with the crack using our Belzona 1161, which is a surface tolerant paste grade putty epoxy. And then once we glued in this bolt, which really at this point probably would have done the job, to have a little bit more extra security, we wrapped around the flange and totally encapsulated it, sealed it off. And once it was cured, they put it back into service, no leakage. So everything worked out there. So we do, you have your standard applications such as holes in pipes, CUI on vessels and tanks, corrosion on vessels and tanks, but we also have some other issues due to just certain maintenance problems and procedure issues with certain flanges and bolts and crevice corrosion. So we can do a lot of leak repair like that as well. So definitely we can use our products in a variety of ways and save you from having to do extensive, repairs or replacements or downtime. So that's our key there, using our products to all they can do. So now I'm going to go into what happens if you can't shut down or if shutdown is just not an option. We have different ways that we can attack live leaks. So one of the ways we attack live leaks is called venting. So it's venting a leak. The key being that you have to fabricate some sort of venting device. So here we were dealing with a tough geometry. We were dealing with a 4-to-6 reducer. We had a large hole here. So we aligned this plate so that the orifice here, the threaded nipple, was lined up right over the hole. We bonded it down with our surface tolerant product, wrapped it, allowed it to cure. All this time, you can see the leak is dripping out. So we're not putting any force on the repair. We're allowing it to cure while the leak is venting. So basically, there's no pressure being put on the repair. Once everything's cured, you cap it off. And then at that point, you can either keep the cap on like that, or you can even wrap the cap. Or if you want access to it later for some reason, you can just, the cap should seal it on its own. At times, we normally wrap everything after the fact. So this is a good technique for large flow leaks or high velocity leaks. If it's coming out and it's shooting out 10 feet, this is normally when you want to use a vented plate. Also, small hairline crack type repairs, it's the venting is a better option. Pretty much the way we work is, you call us with a leak and we come out there and we have different ways to fix the leak. So this is one of our techniques, and it depends on the scenario if we're going to use it or not. This is a pretty high flow scenario. So here, a venting plate was pretty much the only option. So they went pretty extensive here and put a valve on it as well with a large nozzle and a hose to divert all the water away. They bonded it down, strapped it down in place, over wrapped it, wrapped it again, and then once everything was cured, they just turned the valve and sealed off the leak. So one thing with the vented leak is you do have to have a way of diverting the flow. So as you can see, this is another application here. Tight corner on a T, coming out pretty hard. You have some pretty poor metal around the leak. So if you try to plug this or really compress it with a clamp or something, you might make the hole even bigger and you might have more issues. So here we did a quick fab at our shop with some simple thin gauge metal welded on the nipple and dry fit it in the field. Good to go. Bonded it down, put on a coupling with a hose to collect all the water coming out. Once this was set up, we were able to wrap it with our fiberglass composite. And once everything cured, we were able to cap off the top. So this is basically a solution when you're dealing with a high flow scenario, tough access area, but you do have to have that way of diverting the flow during the application because you can't just have it just dripping on you as you're doing it. So you do have to have some way of collecting everything and have to realize that once you install all these things, you have to allow them to cure before you can cap off the vent. So we do have some products that can cure in 2 to 4 hours. So that's typically what we try to use to have the least amount of venting time so that we can, stop the leak as fast as possible. But it all depends on the scenario and what we're dealing with. So then the other way we stop leaks is by just fighting the leak. So we're gonna try to plug the leak with either some sort of mechanical plug or our Belzona Quick Cure products. So something like Belzona 9611, which is a quick cure epoxy stick, or Belzona 1212, which is a quick cure epoxy, or a combination of the two. Our normal procedure for this is to do a minimal prep around the defect, maybe a file or sandpaper. It always depends on the scenario. Are we dealing with a hazardous chemical? Are we dealing with a hot fluid? How bad is the metal? I mean, typically when you're doing the live leaks, you're probably dealing with some sort of water scenario. So you normally get some prep going on. So we'll do some as good a prep as we can. Try to stop the leak with as small of a repair as we can. Once we stop it, then we can put a better composite repair over the top. So what you need if you're going to fight the leak is definitely some surface tolerant products. You're going to have a wet substrate. It's going to be contaminated. It could be oil. It could be doing a floating rooftop tank where you have oil coming out, gasoline. So you need products that can be applied to these lesser than ideal surfaces. So we have some specialty products that can bond to these types of metals. So they're achieved by displacement of moisture. So they can be applied underwater. They displace moisture. They can absorb contaminated oil, and they can penetrate the pores, and they also lock in quick. So we have some that can cure quick, so they can do all this within a 5 minute period. And within 5 minutes, they're already locked in, loaded into the profile. So one thing I do want to mention is whenever you're doing a contaminated application, you still want to prep as much as possible because you want some porosity in that metal, or better word is a roughness. You want to get a rough anchor profile so that your Belzona or your epoxy can get into some grooves of the roughness of the metal and really anchor in there as quick as possible. So this is an application, one of the more impressive applications I've seen. As you can see here, we have a header pipe. We got a couple of leak spots. They use an MBX bristle blaster, which is like a wire wheel on steroids, a specialty made for paint roughness of metal. So it puts a nice rough surface profile on the metal. So they prepped right around the defect, plugged it with our 9611 and a ratchet strap. So they were able to get this 9611 plug, get it into the hole with a ratchet strap behind it to hold it down, compress it, tighten it, stop that leak. Once they stopped all the leaks around their repair area, they reinforced them. After they reinforced them, they went ahead and sandblasted the surrounding area and then installed a complete composite overlay across everything. So, like I said before, your first procedure is let's stop the leaks with localized repairs, reinforce them as best as we can, ensure that they've stopped the leaks. Let's prep the surrounding area, and let's put on something that's really robust over the top of everything. And then finally, my last slide, this is leak prevention. So on the tank here on the left, this was during a shut-in. So this was a turnaround for this tank, and we wanted to make sure that this tank was bulletproof. The one on the right was actually leaking, and we actually had to do a leak repair right here. You can see this red spot here. This is the spot that was blasted and flashed over, and this is a leak spot. So they wanted to make this tank bulletproof. So what we did was we completely lined the inside. So as you can see here, we had DH running and climate control running inside the tank. It contained 92% sulfuric acid, alkylates, and a vapor phase isobutane. This is part of their alkylation unit. So we coated the entire inside to stop any further internal corrosion. Really, the welds were the most beat up on this tank, so the welds were close to popping through, I would say. So we reinforced the welds with some paste grade and lined the whole tank to make it corrosion resistant on the inside. On the outside, we also protected the nozzles with some nozzle inserts. So if you ever have nozzle issues, small nozzles on tanks, we have a solution for you. And then there was some scattered external corrosion throughout the tank. There was actually a hole on the manway that they had a clamp over. So we installed a composite wrap over the manway as well. And we installed some composite wraps on some of the nozzles that were severely thin. And we coated a lot of localized corrosion on the exterior as well. So just a full bulletproof leak prevention and corrosion prevention system for that tank, starting from the inside all the way to the outside. And that was about 3 years ago, and everything's working great. So thanks for joining in. Is there any questions? I haven't really looked at the chat. Feel free to unmute yourself and ask some questions, or if you have another thing going on, feel free to talk about that as well.
Yeah, Alex, do you test your chemicals at higher temperatures?
Yeah, we'll test
the resistance.
So we have a chemical resistance chart where we'll have a variety of chemicals tested at different concentrations and temperatures. So we test from 68 degrees to 194, and then we do some specialized testing above that as well. So yeah, we definitely tested at different temperatures and concentrations. And if we don't have your chemical tested, we can always analyze to see what we have tested and what's comparable. And we have a good relationship with corporate, so they can get the R&D team behind it and look into the chemistry and all that and find a good product for you.
Thank you.
Any other questions?
Yeah, the other thing that sometimes we have go around when we talk about composite wraps here at the site is that elusive fire case scenario. So the product that Belzona has, does it meet those requirements? Have y'all been in that kind of environment with your engineering discussions in regards to these composite wraps?
Yeah, so that's definitely a topic. Our product is not going to handle fire.
Right,
However, we do have testing where we put a intumescent coating on top of our product, and
right,
we went through the 60-minute fire endurance test. I think it's like a fire at 2000 degrees F for 60 minutes,
right.
and then it's pressure tested after that, and it passed. So basically,
Okay.
you have to coat the composite with an intumescent coating that
Right.
protects it and maintains the composite at a certain temperature throughout the 2000-degree fire experience.
Yeah, that
So
makes
the
sense.
yeah,
That
so
makes
as long
sense.
as that, yeah, exactly.
The other consideration that I have, some of our composite wraps we keep on might have an application where it's going to be there for a few years. And I've had some varying success with that where at some type of an interval, I have to get some type of coating applied to protect the fiberglass or Kevlar or whatever's been put on there. Your material, does it need any type of protectant coating to help it not degrade from UV?
I would coat it if it's in the UV. It doesn't really, it'll turn a little yellow and it shouldn't affect the mechanical properties too bad. But I mean, it's easily top coated the next day with any sort of UV product. You can just put it
Yeah,
on top and protect it. It is highly chemical resistant, so I mean, it can handle like chemical spillage on it and stuff like that, or chemical contact from the inside. But if it's going to
right.
get direct sunlight, I would give it a UV top coat.
Yeah, that's the problem I've had with some is that the UV will start to degrade that band of the wrap, and you'll start to see the fibers come
Yeah,
loose, and that's not very encouraging.
yeah, it's a you know, we've had them outside and they just turn a little yellow. I haven't seen it to the point where the fibers start getting exposed, but the
Perfect.
outer resin layer turns a little yellow. But yeah, I would say just the easiest way to fix that is top coat. Put it in the procedure, top coat next day. Um,
Right,
during when you inspect it the next day, just top coat it.
right. And you were saying that these are, definitely engineered devices. So you would say that they meet ASME BCC2, right? As far as the required material and performance properties and all that other good stuff.
Yes, sir. Yeah, they
Perfect.
the Super App 2 is ASME 401, which is the high risk application.
Perfect. All right. Thank you so much.
Thank you. Good questions. Any other questions, comments? If you have any topic you'd like to discuss, anything going on in your plant, feel free to shoot us a message. And thanks for joining in. We'll get you your credit hours and have a nice weekend.